Hi, can you hear me? Hi, Parth, can you hear me? Hello, can you hear me? Hello, Parth, can you hear me? Hello, can you hear me? Hello, hello, yes, okay, good. All right, let's get going. Okay, I'll see my screen. Okay. All right, welcome back. All right, let's settle down. Just a minor change to my office hours. I need to change it to 5 p.m. on Tuesdays and Fridays. So today, starting at 5. Turns out I have another class tonight, and just wouldn't give me time to get home for it. So yeah, I need to move it to 5 later. Other than that, it stays the same Tuesdays and Fridays. All right. So starting today, if you want to come by, there's a link that if you click on that link, you'll I think it's my personal Zoom, right? So everybody can just join that, and we can meet there. All right. So we met on Friday. We discussed how to install MySQL. We downloaded it, we installed it, and I believe most of you have it's working for you. We did get a few folks who were having some issues, and the TAs are supposed to be helping you out. So just reach out to them, and they can walk you through it remotely. But other than that, hopefully by by the end of this week, everybody will have a working MySQL server running on their machine, and we're ready to hit the ground running with the next assignment, where we're going to start actually building the database. First, we'll be designing the database, and then we'll be building it. Okay, I believe it's being recorded, right? Yeah, it's recording. All right, so let's talk about the next week, this week number 2. So the first focus of starting any project is to design whatever it is that we're building, right? And it's no different with databases. Oftentimes, software engineers are too enamored with the technology, where we love this language, we love these tools, and we're ready to start coding, right? We can't wait to start creating all sorts of coding and starting to see it work, compile it, and so on. But oftentimes we have to first sit down and agree on what it is that we're building, right? And a lot of those skills and techniques come from other software engineering fields, right? And there's a whole course that I don't know if you've taken it, software engineering and designing. Probably you've taken Fundies, and you've taken some of these other previous courses where you start thinking about how is it that you model things, how do you create a data model for what it is that you are building, that you want to capture the data for, right? So same thing. We want to be able to apply many of those techniques and many of those concerns, right, of designing what it is that we're building before we actually start coding. Right? So this week we're going to be spending some time on what are some of those techniques. We'll review some of those concerns or issues that software engineers go through in actually building the design, right? And then how do we make that into a formal description, right, using a graphical tool, and then how do we convert that into actual code that we can turn into SQL or Python or Java or whatever language that is that we're building, right? So yeah, so we'll spend some time in use case analysis. We'll focus more on UML class diagrams, and this week's assignment will be let's start designing things, right? And usually it entails in reading some very vague or very contradictory description in English, right? English is not a very good language to or any language for that matter. It's very contradictory. It's vague. It's words have different meanings depending on the context. It means something or another, or two words mean the same thing, but it's completely two different words. And so we need to be able to formalize that, right? Go from that vagueness into something more concrete. Very often we interview our clients and they'll ramble on things that have absolutely nothing to do with what it is that we're supposed to work or build, and completely skip over the things that's very important, right? Because they'll assume that you know certain things, which you don't, okay? Or even you might have worked in many different projects before, and you have this baggage that you bring with you, right? All these assumptions, all these biases that you have from having worked in previous projects that you want to then apply into this new project, right? And humans are very bad at analyzing things. We reason by analogy, right? If it worked here, well, it must work here, over there, right? And so we have to work against our own biases of what you might know, and see if we could come up with something new. But oftentimes to come up with something new, you need to know, well, what else other people have done, right? And what techniques are there? Can we make it better? So let's spend some time talking about use case analyses. Use case analysis is somewhat tangential to what us software engineers use. Some of the techniques I'm going to present here, these are mostly techniques that a business analyst might use, right? Business analyst is a wannabe software engineer, maybe, who knows perhaps about the technology, but not enough maybe to actually code it. But then they know about the technologies that are out there, the techniques and the challenges that software engineers go through about actually building things. But they take the brunt of meeting with the client, right, and presenting gathering the requirements from the client, and then presenting those requirements to the software engineer, and the software engineer actually has to build this, right? A good software engineer knows about the technology, knows how to say no to the client, knows when things that are oftentimes one of the biggest problems of a bad business analyst is that they'll say no to something that because they think it's hard, right? And they'll say yes to things that are actually very hard. So they don't know if something's really easy or hard, right? And they'll make some certain assumptions based on if they were building it, and it's not, right? So let's just look at some of the things that a business analyst goes through, right? So usually they meet with clients, and they through out several meetings, right? Several sessions, and might bring somebody from HR, somebody from engineering, somebody from finance, they might bring in the CEO. They might bring all the folks that are interested in a particular project, right? And everybody is saying their piece, right? And everybody has some contradictions of what it is that the project that they're building needs to be. Somebody have a different understanding of how the process, even within the business, works, right? And so it's the job of the business analyst to facilitate these meetings, gather all the requirements from everybody, and then have a single document, right, that captures all this information, right? Then usually there's a software engineering that know how to build stuff to build perhaps some really simple prototypes, right? Where they just put together a couple of either PowerPoint slides or some really quick HTML pages, right, for the client to play around with. Is this what you want us to build, right? And they gather more requirements, right? And so this process many consider to be the time when any project is at its biggest risk, right? You could always, oftentimes you can determine when why a project failed or succeeded, based on what was decided very early on in this phase, right? Of gathering the requirements and everybody agreeing what it is that we're building and what we're not building. Okay, and it's a very, very hard thing to do. Business analysts, they have to deal with the actual folks, right? The actual clients, and their requirements might change. They think they want something, but they really need something else, right? And they might love something, and as they use it more, they hate it. The more they use what they asked for, right, the more they hate it, right, and realize that that's not what they wanted, right, or that's not what they needed. So this is all very, very hard to deal with. Anyway, they come up with all sorts of business rules and quality attributes that you want it to be pretty, you want it to be usable, that you can maintain it, right? That folks can understand with the system, how it works, that it's portable, right? I mean, a lot of decisions on, well, should we go with MySQL Server or Oracle or should we go with Java or Python or C#, right? And so all these questions early on, can I change my mind later, right? If I go with one database, can then I change it to something else later on, right? All these decisions are being made very, very early on. Can I port it? Is it portable? Can it scale? Does it work for 10 people, but then is it going to work for 100, for 1,000, for 1,000,000? No, are these things is it going to scale? Now these meetings, business analysts are very keen to make sure that they try to understand what the goal of the user is and understand who is going to be using the system. What are you trying to solve, right? And based on these users, they keep track of all the different goals that they want to try to achieve from the system, right? I want to be able to create an order, or then I want to be able to fulfill the order, and I want to be able to track the order. Right? I like to be able to filter all my orders based on certain criteria. Right? So as they gather all these requirements, that is going to drive, right, how the data about orders is going to be stored in the database. Right? Every decision that you make about either I'm going to split this table into 2 or 3 or 4, and the attributes that you're going to put in what the data types is going to be always going to be based by what it is that the goals are of the client, of the user, the end user. The end user needs to be able to do these things. Well, that means that we need to capture all that data, right? We need to be able to filter it and query it and store it in a certain way. Yes, all driven by business rules and business needs that are based on actual users that are trying to accomplish something with the system. In a system, right? Oftentimes it's very useful for the early on to decide what is the system. So we'll put a box and say anything that's inside of this box we're building, anything that's outside of the box we're not building, right? And it's very important to determine. Is it data? Am I going to be tracking this data, or is data that lives outside that someone else is building, right? That I can connect to. I can connect to the FDA, or I can connect to whatever online data source that I can connect to, right? And I'm not responsible for that, right? I just can connect to and get it. But then we want to know what it is that we're building. We need to decide who the actors are. Who are the folks that are interacting with the system, right? If it's a restaurant application, well, you need the cook, and you need the server, and you need the actual customer, and the person who's delivering this, right? Everybody's using this app, and depending on who you are, right, you're going to need certain buttons or certain user interfaces and certain things that you want to be able to accomplish, right? I've delivered the pizza, right, and now I'm going to the next one, and somebody gave me a tip, or somebody gave me a feedback, or so all these things. Are we capturing all that? Yes, and that's going to drive the rest of the design. And so the use cases is the set of all the goals that a particular actor wants to achieve, right, within the system. Use cases are, these are all the different things and different goals that a particular user wants to be able to achieve, right? Again, if you if you're the server, or if you're the delivery boy, or if you're whatever you are, right? These are all the things they need to be able to do, and it needs to be represented in some kind of user interface. It needs to be represented in some kind of table, records, and relationships between in the background. So here's an example of what those use cases might look like. You have the full name of the use case, and the use case might be fulfill an order, or or search orders by date, or delete all the orders that are cancel or something, right? So those are the use cases. You describe in English, in plain English, what is describing the goal of the user, what are the preconditions, right? That whether you need to be logged in, and you need to have a particular role, or that you have to be able to be playing a particular part of the organization, and then all the different steps, right? It means that if you want to cancel the orders, well, you need to be able to give me some criteria, maybe a starting date, an end date, right? And then you can maybe search by a particular status of the order, right? And search it by maybe by quarter, or by whatnot, right? So these are all the steps that the person would do to facilitate, and then one of the post conditions it'll be that perhaps the system lists comes back with a query with a collection of all the orders that meet your criteria, right? Or that if you are deleting it, then it means that okay, you've removed all the orders for that criteria. And so this is a collection of these things. Goes into a formal requirements document, that the business analyst is responsible for, right? And then that goes into like a contract between what the client wants us to build and whoever's going to actually build this, right? And they would create a purchase order, and we create a whole bunch of work orders, and folks actually start to build this, right? And this is given to software engineers. That some of them are front-end developers. They're going to come up with all the wireframes of what the user interface is going to look like, and then the back-end engineers, right, are going to start thinking about, well, what classes do we need, and what tables do we need, right, and what records, how are they going to point to one another, okay? All based on these requirements. That's going to drive everything else, right? Everything that you build is within the context of some business requirement that needs to be solved. Usually these requirements typically will have a name, and will have a number attached to these. And usually, as you're building classes and building software and building all your source code, right, typically will be attached with a requirements number, right? All the stores that you build, all the tables that you create will be based on this number, so that there is a direct correlation on the work that you're doing and that you're being paid for, derived from actual requirements that the client is asked us to do and that they're paying for, right? And this, you can audit whether what progress you've been making, right? How far are you into the project, and you can and then you can make projections on where you're going to be done, right? If you need to hire more folks or not, or whatnot. Yes. Anyway, so this is the realm of business analysts. There are different templates on how to build these things, and different companies will have different templates on how to capture this information. Some more formal than others. Now, typically this goes into some huge to-do list. There's plenty of very popular task management applications, such as Jira. I don't know if you've had a chance to play around with Jira, where typically all these requirements, all these are converted into user stories, right? Into where you describe what the particular person that they want to achieve certain things, what the steps that they're going to do, and what the actual result of the story is, right? And software engineers take all these scenarios, all these user stories, and they go out and they build these things. Okay. All right. So here's just examples on use cases, right? So if you're on Amazon, you want to be able to track the order, you want to change the shipping, change the billing, you want to check the status, cancel an order. Online purchases, you want to add things to a shopping cart, you want to search the catalog, you want to check out, you want to pay. These are all different use cases. and this is going to drive, right, all the creation of the data models and the tables and the classes and everything that's going to happen, right? Everything happens within a context, right? I'm just skipping through these. I'm just going over some of what happens really in industry. Anyway, so the business analyst comes up with a diagram such as this, where they capture all the folks that are using your system, right? You know, this was a system where the social network for fishermen, right? And you know, and there's a person who wants to go out fishing this weekend, and they want to be able to rent a boat, right? And they want to buy the tackle, and they want to buy all the things that they need, and they go out and they want to keep track of what they caught, and the wind speed and the temperature of the water and the weather and whatnot, right? And just people that are advertising. So people want to be able to plan a trip. They want to search for locations. They want to create the gear that they're going to take, right? All the different fishes that they caught. So as a business analyst, they document all the different things that need to be done, right? And this is an input into us, the ones who are going to build this, right? We're looking for all the verbs and all the nouns, right? If you say that, oh, there's a gear and there's a profile, there's an account, there's a trip, there's a location, there's a product, there's a store, right? There's ads, right? All these nouns are clues for us, the data analyst, right? That says, oh, well, I need a table to capture the gear and the fish and the trips, right? And all these products, I need to capture all these things, right? And the verbs, right, are going to be useful for us to declare what are the relationships between these, right? How are these related? You know, is the fish related to the trip? Is it related to the gear? So yeah, I caught this fish. I caught it with this gear, right, in this trip, right? That was part of the plan that I went out with my buddies this weekend, right? So how are all these things related? Oh, well, we're gonna need all these foreign keys and primary keys, right, to relate all these records with one another, right? It all starts here, right, with somebody having gone through this exercise of having done a use case analysis. Okay. Yeah. So I just wanted to put, you know, in context where things might start. Right. You're not going to be asked to do any of this. You can assume that I will be your business analyst. Right. I'll be your business analyst. I will have done an analysis, and I'll give you the result of that analysis, and then you go off and build it. Yes. Oh, it's not available? Okay, let me make that. Sorry. Oh, it's not. Thank you. Right. So yeah, you can assume that I will be your client. I will be your business analyst, and you're working for me, right? And so you can assume that I've made certain decisions already, right? Certain assumptions, and then you can go off and actually build these things. Make sense? You know, I just wanted to set that context. Excellent. All right, so these diagrams, right? These diagrams are called use case diagrams, right? And they literally look like this. You know, these ovals and lines and folks. Here's another example of an online course management where you have students and faculty, right? Those are two actors in an online learning system, such as maybe Canvas, right? Or God forbid, Blackboard, right? Where they each user has a different goal, right? And they can do certain things, but not others, right? So a student might, you know, they can view their grades, they can enroll in a course, they can take an exam, they can work on a project, right? They can complete an evaluation. As a faculty, right, I can create evaluations, right? I can create the courses, right? I can prepare an assignment, I can prepare a quiz, right? Prepare a final, grade an assignment. So each one of us has, we both are acting on the same data models, but we have different use cases for that same data model. You know, whereas I can create a quiz, you can't create a quiz, right? I can delete a quiz, I can edit a quiz, right? I have a whole bunch of things that I can do with a particular data model, and you can do other things with the same data model, right? You can take the quiz, right? You can give feedback on that quiz. You can contest the grade on that quiz, right? But you can't edit the quiz. You can't delete the quiz, right? You can view and take the quiz and whatnot, right? So the data model that we build needs to be able to fulfill all the different use cases, right? And the use cases allow us to drive and say, okay, well, does the data model that I'm creating, does it support all these features? Make sense? All right. So you'll see a lot of these, in industry. All right. So the use case diagrams is one of many types of diagrams that we'll be looking at this semester, right? The other type of diagram that we're going to be using quite a bit this semester is UML class diagrams, which I believe you've seen this in previous courses, if I'm not mistaken. So UML class diagrams, right, is part of several graphical language that called the Unified Modeling Language, UML, right? And UML has become kind of like the standard graphical language for engineers to be able to talk to one another, right? Regardless of what your preferences is in language, right? If you prefer C# or Python or Java or whatever language you prefer, UML is the lingua franca, right? We can all understand UML, right? And we know that each language will have its own small idiosyncrasies, right? And has its own particular dialects and whatnot. But we can all come back to UML and have an equal discussion, right, on what it is that we're talking about, right? And what we want to be able to do is be able to represent the data in a formal way, okay? And there's actually many different ways that it can be represented depending on the technology stack. Where are you in the technology stack, right? It can be represented in English, right? It can be represented in SQL as a table. It can be represented as a Java class. It can be represented in an XML document, right? And so we want to be able to represent them all in a unified way, right? And then we should be able to convert them. We should be able to, if we agree that they're equivalent to one another, it's just that the language is different, right? We should be able to convert them into any other equivalent representation. Yes, right. In fact, there's some tools, they're fairly expensive, that you can start off with UML, create a UML diagram, and then say, okay, well, generate the Java for me, right? And boom, we'll generate the Java code for you, okay, that already represents your data model. Right, you can say, or export it and generate the SQL for me. It'll generate all the tables and all the foreign keys and primary keys for you. Okay, and you can just say, I want it in C#, I want it in whatever language you want, in JSON, in XML. It'll export in whatever data representation you want, right? Starting from one single unified representation of the data model. Make sense? Right. So whenever you're going to start designing, UML is a great place to start. You can always then convert it into whatever you want. Okay, it can also do reverse engineering, right? It can look at a C# code, right? And it can look at all your classes and the inheritance trees, right? And the overloading and abstract classes and whatnot. It can do reverse engineering on your code and then generate UML class diagram, okay, which is pretty cool, right? It understands your code and it gives you graphical representation of your code. And then you can say, well, now generate a Java version of this. Right, and it'll do the conversion and generate Java. Now do the XML representation. Now do a SQL representation, right? And boom, you got a database ready to go for that particular language. Right, very, very cool. So you can do forward engineering, reverse engineering, all the way through. Some very expensive tools, but they're out there. So yeah, so different infinite ways of representing, right? So in Java, C#, C++, XML, JSON, CSV, spreadsheets. Right, and so we're going to stick to UML as our starting point, and we want to be able to go between these different worlds of ways of representing. We can represent it in English. Actors are cast in a movie. Well, we can capture that formally, right, in UML as two classes, right, with an association, right, and the name of the association, and then star and star, right. One actor can be in many, this means many movies, and one movie can have many actors, All right, that's the formal representation of this English phrase. Yes, it can also be represented in Java or C#, right, as two classes, actor and movie, and both of them having an array of movies or an array of actors, right, as a many-to-many pointing to each other, right, where movies is going to have a reference of many objects, pointers, pointing to many instances of movie, and movie is going to have an array of multiple instances of actors pointing to different objects of actors. Yes, right. And in SQL, you would have something like this. You might have a table where you list all your actors, a movies table where you list all your movies, but now there's no way for them to refer to one another, right? You can have maybe a foreign key of a movie pointing to a single actor. But that's not what we want, right? We don't want a movie pointing to a single actor. We want a movie pointing to lots of actors, kind of what we have here, right? One movie pointing to lots of actors. Well, we don't have that in SQL, right? We don't have the array, right? An array of foreign keys. You can have maybe one foreign key, right? Or maybe a specific number of foreign keys in a table, but you can't have like an unbounded number of foreign keys. There's no such thing. All right, so the equivalent might be to have an intermediate table, right? An intermediate table that has two foreign keys, right? Two foreign keys, one that points to an actor, and one that points to a movie, right? Saying that, so you could have for every row, a row would say, well, this actor here is in the movie, right? And this other actor is in the same movie, or maybe some other movie, right? So this allows me to create any number of associations of any movie with any actor. Yeah, any movie with every actor, right? So this allows me to create a many-to-many. So this is considered like a mapping table, right? That it's mapping an instance of one record in the actors with another instance of a movie in some other table. Make sense, right? Yeah. So and I could go on here, right? There's an XML representation. There's a JSON representation. Right, there's a CSV representation, there's a spreadsheet representation. There's an infinite ways that we can represent the data. Yes.
What's the need for having the foreign keys and the actual
You mean here? Oh yeah, no, these are the actual fields. The fields, so these are the ones that are holding the actual value, right? That is pointing to which is either this value or that other value, these two. This is just saying that field there is a foreign key. Yeah, it's saying actor ID is a foreign key, and it's referencing this table, the field ID in that table. Yeah, we call this a constraint. We're saying that we're saying basically that this is not just any integer, right? I can't just put any value in there, right? I'm saying no, constrain it. Meaning if I have actors 1, 2, and 3, right? If I just say that this is an integer, I could put a 4 there, right? Or 10, and that's fine, right? But it would be bad data, right? And what we want to do is we want our databases to help us avoid entering bad data, right? Things that are impossible, right? So we constrain it. We're saying no, this is a foreign key that its value can only be a valid value in actors.id, meaning you can only put here the values 1, 2, or 3. You can't put 4. It would stop me. There is no actor with ID 4, right? So it would stop me from doing that. Make sense? Yep. And constraints allow me to make sure that the data that I'm entering is good. All right. Make sense? Everybody good? All right. So we want to be able to learn how to go between all these worlds, right? First, we're going to get started with this, right? With UML. How is it that we design it? A good database design starts with a good class diagram design, right? So we'll start there, and then we can just push a button, right, and just generate the equivalent. The equivalent anything. The equivalent Java, the equivalent C#, the equivalent SQL, the equivalent English. Yeah, I guess so. Yeah, the best approach of developing programs, you design at a very high level using UML, right? And then you then start to convert it into the Java, C#, C++, right, or convert it into SQL or an ER model, right? And then we start off at UML. All right, so let's talk UML. Let's talk about classes and objects and instances and whatnot, right? I'm sure you've covered classes plenty in other languages, right? I'm just going to review some of it and what are the quirks that we're going to be using in this particular class. Yes. All right. So we say an object is a particular instance, right, of a class that has an identity, right? Usually because it's some instance that was instantiated from memory, right? And it's using some particular address in memory, right? So it has, by definition, it has an identity, right? And we say also that an object has a state, and the state is based on the values of all the attributes, right? The values of the attributes make up the state of that object, right? So if it's an account, the state of the account might be its balance, right? And the balance changes over time as you deposit and withdraw, right? And you want to know what the state is at a particular time. The way we refer to it, the way we represent classes is with a box, usually with 3 different sections, right? One of the sections is the name of the class. That name usually is a noun. It's singular, and it's capitalized, right? Or at least camel cased, right? Where the first letter of each word is capitalized. Yes, right. That's the naming convention that we're going to follow with classes. Notice that it's different from the naming convention on tables, right? We said tables. The naming convention of tables is that it's going to be lowercase, right? It's going to be plural, and if it's a compound word, we're going to use underscores. Yes, right. Here, the naming convention is slightly different. Names are camel cased, right, and they're singular, but they're still nouns, right? Then you have 2 other sections. One is attributes, and the other one is methods, right? The attribute section describes all the fields or all properties that make up or describe your class, right? Where if it's an employee, you might have first name, last name, salary, date of birth, the date of hire, things like that. Yes, all the things that describe your employee. Make sense? Plus the data type, whether they're strings, numbers, integers, floats, dates, booleans, whatever. Yes. I'm sorry. Well, we use the word parameter for like functions, right? When you pass some values, when you parameterize a function. So no, we usually use like properties or attributes. Yep. And so yeah, so definitely these are used. We're going to be using definitely attributes, definitely data types. Knowing the naming convention, it's a colon and then the data type. These are accessors, right? They're public, private, and inherited or protected, right? And we're not going to be using that in this particular class, right? But they're super important, right? If you're implementing this in Java or C# or any programming language, right? Whether the attribute can be accessed from outside, right? Or it can only be accessed from within the class. That really has no bearing in data analysis and in our database course. So it's optional if you want to put it in there or not. Okay, you're not going to be penalized if you don't put in, right? And you're not going to get extra credit if you do put in. So yeah, the other thing is that these are methods. Methods are super important if you're coding this in Java, C# or any object-oriented programming language. We're not doing that. Okay, so we're not going to require methods, right, in this class. Yes, right. So the only thing we're going to care about is the name of the class, the attributes, and the data type. That's all we care about. Yes. Constraints typically are the lines, right? When they go between one class and another class, they're implied in the line. Like for instance, a foreign key and a primary key, that means that there's a line between 2 classes, and we'll see that in a minute how it converts. Yep. So here's an example of a person class that has a username, a password, date of birth, email, and phones, right? And they're all private. It's a good practice to make all your attributes private in general. Although it doesn't really matter for our database. Some strings, some dates, phones. Notice that these are all primitive data types: string, date, string. Phone presumably is a custom data type, perhaps another class, right? And in that class, you can have maybe area code, country code, and the actual number, things like that, right? That make up the phone. So it's a compound data type. Okay. We also have multiplicity. If you notice these brackets here, tell you how many of instances of phones you might have, right? So this might say that you could have 0 phones, or you can have many phones, right, associated. So this could be typically implemented as an array, right? 0, 1 means that this is optional. Maybe you don't have a date of birth. You're not born yet, or you are. I might have this information or not, meaning it's not required. If I don't have the value, it's okay. If I have it, that's awesome. There's the cardinality has the nomenclature for the cardinality is that it's square brackets m and n, or m is it's a minimum value and n is the maximum, right? So what's the minimum number? What's the maximum number? So you might have maybe a car might have at least 3 wheels, maybe, right? And it could have maybe even more than that. If it has less than 3, then it's a motorcycle, right? And so you can establish what's the minimum criteria for the multiplicity. We also have enumerations that look like classes, but they're not classes, right? They're definitely not classes. They, the same thing. They have a box, they have a name, right? But notice that it has the pointy brackets at the top. See that, right? We call that a stereotype, meaning that to distinguish them from classes, right? To make sure that you understand that this is not a class. You should not treat it as a class. Right? We use what is called a stereotype at the top, and we say that this is an enumeration. Same thing, you give it a name, but then the values here, these are values. These are not attributes. Right? This is not a variable, right? We say that these are the only valid values, right, for this data type. So, for instance, say you have a movie class, right? You have a movie class, and you want to capture the title, the plot, right? Who the director is, and you want to capture the genre. Yes. And so for the director, maybe you provide for the plot or for the title of the movie, you use maybe a string data type. Yes, that's appropriate. Now, what data type would you use for genre? Say you use string, right? That's the most common thing that I would use, right? It's a genre. You can type whatever you want for that genre, okay? And what values would you expect there? You would expect, somebody might say drama, comedy, sci-fi, fantasy as a genre, yes? But what if you start looking through your database, right, and you start finding, things that have absolutely nothing to do with this, with the genre, right? And you find maybe brands, right? Like Ford, Honda, GMs, those are not genres, right? They're brands. But was there any way that you could stop folks from typing a brand? You could not stop it. It's a string. You could type anything you want. Yes. So ideally, what you want to be able to do is create some kind of constraint and say, no, the only valid values that you could possibly type here are these. And the way you would implement them is you would create an enumerated data type, right? And you would create movie genre, and you would say, okay, well, the only valid values for the data type for the genre variable is not string, right? It's movie genre. Okay. And you would say, well, movies, now it's not a string. You would use this data type instead. Make sense? All right. We actually we use the enumerations quite a bit. If you say an integer, you say if a variable is an integer is an enumerated data type, right? It goes from minus infinity, right? All the whole numbers that go from minus infinity all the way to 0, and then all the whole numbers that go from 1 to plus infinity, right? It cannot be 2.5. That's an integer, right? So that's no good. Yes. Yeah, same thing. Just so you would expect that in programming languages, there's a max int, max int. Yep, same thing. So yeah, so we already use lots of these enumerations, but you can create your own enumerations. There's also inheritance, okay, where you want to be able to establish a a mechanism for reusing things that you have already declared. Okay, you might find that there are certain nouns that you're describing, and you start noticing that some of the nouns are special cases of other nouns, right? For instance, you might have the employee, right? You capture an employee class, and that employee class, well, you have all employees have a first name, all employees have a last name, social security number, the data that I hire them and whatnot. Yes, but then as you start entering your data about the employee, you start noticing that, wait a minute, now there's a special edge case here where most employees are full-time employees that have a salary, a yearly salary, and I like to calculate their monthly payment or biweekly payment by dividing the yearly salary divided by 12 or 24, and then I know what to pay them every month. Yes, right. But then now I have this other employee who's not a full-time, right, and they're actually a contractor, right, and they get paid differently. They get paid by how many hours they work. Okay, and well, one solution that I could do is that in the same table, the employee table, I'll have a field called yearly salary, and then another field that says hourly salary, right? Okay, but as we'll see later on, this is breaking one of the normalization rules, right? Is that if you are an hourly employee, I'm going to fill out your hourly rate. But if you're a full-time employee, I will fill out your yearly rate, and the other one will have to be null. Yes, it makes no sense to have both of them in there. Yes, right. As we'll see later on when we talk about normalization, a better solution would be to split these into two tables, right? Split them into two tables. One of them specifically for all employees. Actually, no, three tables. You would have one table that has all the information about all employees, and then two dedicated tables, one for full-time employees and another one for hourly employees. Make sense? All right. And for every type of employee that I come up, maybe I have a commissioned employee, right, who gets maybe paid a very low base salary, but then they make a huge commission whenever they make a big sale, right? They get 5, 10, 15% of whatever they sell, right? They're paid completely differently, right? So it depends that they 1 month they get paid a lot, another month they get paid very little, depending on how much they sell. So now I would have maybe another table that captures that information about all commission employees. Make sense? Well, the way you would capture that in UML is that you might have a base class that captures all the fields about all employees, right? First name, last name, social security number, blah, blah, blah. And then you would have your specific classes for the full-time employee and for the and your hourly employee and whatnot, right? And you use inheritance. Inheritance means that all these fields inherit all the fields from its parent. So all full-time employees and all hourly employee, they have all these fields. They all have the first name and the last names and date of birth and social security number they inherited. Plus, they add specific fields that are specific for that type of employee. Make sense? And this type of relationship here, we call this there's two names for this. One is either specialization, meaning these are special cases of that one. Or it's also called generalization, right? Meaning that this is a general case of these. It depends how you look at it. If you look at it from the bottom, that's a general case. If you look at it down, right, it's a special case. Yes. It does. Yes, you're right. It shouldn't. Yeah, that's a typo, right? It cannot have a width that I already have over there. Good catch. Yep. Yeah, width would be inherited from widget. Yep. Make sense? Everybody good? All right. And we also, if you remember, we also say that these diagrams, we say that there is a they implement an is a relationship, meaning an image is a widget, a heading is a widget. an hourly employee is an employee, right? All right, let's keep going. Multi-valued valued attributes, meaning attributes that can have multiple values that can be implemented as arrays, right, of how many values you can have. You have associations, right? Now, all we've seen so far is about a single class, right? But one single class or one single table would be a very boring database. Typically you will have dozens of tables, hundreds of tables, right? And you would have equivalent, dozens, hundreds of classes, right? Like for instance, you have authors and books, right? Two classes, and a line between them is called an association. They're somehow associated to one another. Yes. Yep. They're both implemented as arrays. Yeah. So authors and books have the way we capture the association is just that we draw a line between the two, right? Optionally, we write also a description of what the association looks like from the point of view of one of the classes. So we say that an author writes a book, or a book is written by an author, right? And notice that the classes are nouns and the lines are verbs. See that? Okay. And that's very important because as we interview our clients, they'll spew out tons of nouns, tons of verbs, and noun phrases and verb phrases, right? And those are going to be our clues. That's going to be our clue on what classes and what associations we're going to be drawing. Yes. Most of the time, the associations will be binary, where two classes are related to one another. Sometimes they'll be ternary. They're going to have three classes that are related to one another. Sometimes four. Four different things are related to one another, and we have to be careful at parsing out those phrases. Is this a relationship between these two nouns, or is there a relationship between the three nouns? Yes, right. And depending on how we interpret the phrase, we come up with different designs. And oftentimes we're going to have to go back to our client and say, did you mean this? Is this related to this or not? Yes, we'll need clarification on how to parse the sentences, right? Because as we'll see soon, we'll notice that if we interpret it one way, we'll come up with one design, a flawed design, right? And if we interpret it the way it's supposed to be interpreted, we'll come up with the correct design, all right? And so we have to be careful. So yeah, this is a binary relationship between an author and a book. An author writes the book, and a book is written by an author. And yeah, and it helps us read. Presumably, this diagram came from this a phrase like this. A book is written by an author, right? Or an author writes a book. Having us read that in English, we come up with that formal graphical representation. You can also have multiplicity not only in the attributes and properties. You can also have multiplicity in the associations as well. How many authors participate with how many books. We can put the cardinality. We can call it multiplicity or also cardinality next to the class, and we say that 0 or more authors participate with one or more books. Okay, and we'll see that there's quite a few types of multiplicities, and how is it that they're how do we read them? For instance, let's take a look at some of the more common cardinalities or multiplicities. Right, here's one of the easier ones: one to many. Right, this is one of the more common ones. One of these is related to many of those. Right, and so you would say one person, an instance of a person, can be associated with 0 or more. The star means 0 or more, right? Or any number, 0 or more phones. So maybe they have no phone, or maybe they have a lot of phone numbers. Okay, they might have a fax. They might have a landline. I don't know who has landlines. Or there's a many to many. Right, where you say that one actor can be associated with many movies, and one movie can be associated with many actors. So this is another very classical a multiplicity between classes, many to many, right? Now typically, depending, so we'll talk about this in a minute, but depending on your audience, right, or how are you implementing this, all right? The way you would capture this, or the way you would implement this in Java, is that the actor would have maybe an array of movies. Yes, that's how you would implement this, and the movie would have an array of actors. Yes, but that's an implementation detail, right? It's a implementation detail of Java, right? Same thing. The way you would implement this in SQL is that you would have to have a mapping table in between. Yes, that would point to the actor and point to the movie. But again, that is also something that is specific to the way you choose to implement this. Whether you go SQL or C# or Java or XML or whatever you choose, each particular technology stack will have its own idiosyncrasies. Yes, right? Here at UML, right, we're trying to get away from the idiosyncrasies of a particular language, of a particular implementation. Yes, right? So just by drawing this line and saying star and star, that's all we need for saying that there's a many to many between these two. Okay, it would be redundant in UML for me to put a variable called actors and say it's an array of actors. It would be redundant. Okay, now oftentimes we put it in there nevertheless, right? We put the variable in there with an array, even though the line is enough, right? But we add it anyway for clarity, right? Because we know that the person who's going to read this is a Java developer, right? And we can establish, hey, you're going to implement this many to many using these arrays. Make sense? Right. So depending on the audience, you might go ahead and actually add certain fields just because you know that is going to be implemented in a particular technology. Make sense? But from the UML's point of view, from a conceptual point of view, you don't really need the arrays. That's an implementation detail. Same thing with if you add here an ID field. Yes, the ID field, do you really need an ID field in Java or C#? You don't. The object is already unique. Yes, it is unique because it lives in a particular memory space. Okay, if you put an ID, it's because you're trying to say, oh, well, this is going to be implemented in SQL, and I want to have a primary key. Yes, right, or I want a foreign key. And so if you put fields here for the primary keys and foreign keys, that's an implementation detail of SQL. Yes, it would be redundant of putting those fields in UML. But nevertheless, you would put them anyway, just because you know your audience who's going to read your diagrams are going to be a data analyst, right, or some SQL person, and they would love to see those fields listed here. Make sense? Right. So you will often see me either putting the fields, not putting the fields. Okay. Sometimes I'll put it in there, sometimes I won't put it in there. I'll remind you, right, that depending on the audience, depending on the technology stack, we might put it or not put it in there. Make sense? Right. I'll make this point again. I'll repeat this point over and over and over. Right. From UML's point of view, I don't need to put foreign keys and primary keys because it's a SQL implementation, and I don't put arrays here either because that's a Java or C# implementation detail. Right. The lines between these two is plenty. Make sense? And also, it also allows me to leave it somewhat vague of what the implementation is. Oftentimes us developers, because we're so enamored with a particular language or solution that we've used before, right? We kind of we kind of have this tunnel vision, right? And are not open to tons of other things. When somebody asks us to do something or to build something, we already start thinking about implementation, right? And that kind of like you start thinking about all the complexities or implementation details, and why would this not work, or why would this other thing would not work, right? And kind of close yourself to many different possibilities. So we have to try not to to fall into this tunnel vision, based on a particular technology that we are familiar with. All right, so here's another example. Yeah, for instance, here it is, right? So somebody comes up with this, right, and says, okay, here's actor, here's a movie, the title and the plot, and here's actor, star and star. That's a many. And then somebody said, okay, well, I'm going to implement that in SQL. And you realize, oh, I can't implement that. I can't just have a table actors and a table movies. I can have the title, I can have the plot, I have the first name and last name. What do I do with this line? How do I implement that line? Right? And we saw earlier, we talked about that, yeah, the way you would implement it is that you need an extra table in there somewhere, right? That points to the actor and points to the movie. Now, from UML's point of view, this line is plenty. You don't have to do anything else. But because you know that there's no way to implement this in SQL, you have to go a little farther. Right? We need to, how do I make this conceptual drawing into something that is more concrete that I can actually implement, right? And the way we went is that we added a separate table. Yes, that's what we did. We created a separate table that, so we converted a many-to-many, we implemented by creating two one-to-manys, right? Two one-to-manys, right? Where here I have one actor can have many entries, and those entries of actors, and here I can have many entries of movies, right? And in both cases, I would have a foreign key that points to the actor and a foreign key that points to the movie. You see that, right? So realizing that your conceptual design, your conceptual diagram cannot be implemented in your particular technology stack, right? And then converting it into something that is equivalent and that it can be implemented, we call that reify, to reify a diagram, meaning make it more concrete, right? So that you can actually implement it. Yes. Yeah, no, I called it casting as in an actor is cast in a movie. Yeah, it's not the term casting as in programming casting. Yeah, no, it could have any name. Another popular name for these kinds of tables is actor to movies, right? Like a mapping table where you have what is mapped to what, right? I'm mapping actors to movies. That makes sense, right? So going from this abstraction conceptual diagram and converting it into something equivalent that can actually be implemented in SQL, we call that to reify the diagram. Okay. And we're only doing it again because we know the constraints in SQL. And we're actually going to be doing lots of these kinds of things that, oh, I can't implement that in SQL, right? Like inheritance. How would you implement inheritance? Right? SQL doesn't support inheritance, right? So there are alternatives on how is it that you would do this, right? Because that would mean that I have some information stored in the employee table, some information stored in the full-time employee table, right? Some information in the hourly employee table. Well, how do they know about each other? Right? You need to have foreign keys everywhere, right? And you need to join them together to then implement to retrieve the actual employee. Some information lives in the employee table, some information lives in this other table, right? So yeah, so we'll do lots of those. Okay, so here's another a little bit more modern diagram called the association class. Okay, so the association class plays the same role as the mapping table we saw earlier. Okay, the mapping table we saw earlier, this is the casting table. The casting table. Now the fields you would expect here are just what? A foreign key that points to the movie and a foreign key that points to the actor. That's it. Right, saying that that actor is in those movies and that movie is in has those actors. That's it. We call it a mapping table. Yes. And this is how you would draw it. This is how you would draw it. Now there's a concept of creating not only the association between actor and movie, but you want to be able to maybe capture some information about the casting. Maybe you want to capture that, hey, that actor in that movie, they won the Oscar, right? And they got all these awards, right? And they got this rating in Rotten Tomato or whatever, right? Okay. That means that not only are you going to have the foreign keys, but you're going to have other fields here describing the relationship between the actor in that movie, right? Now, this is not just a mapping class, right? We call this an association class, right? Not only are you describing that these two things are associated or related, but now you want to describe that association. So we don't draw it like this. We don't draw it like this, although we could get away with this. The old version of UML, this would be fine, right? This is how you would draw it, and that's totally fine. In version 2.0 and above, the way you would draw it, instead, you would draw it like this, okay? Where you have the two classes, same thing, many to many, yes? But instead of drawing it in the middle, you know, and drawing it with two one-to-manys, instead of drawing like that, right? You draw a line between the two classes and then a dashed class, right, with the association class, right? Which would have the two foreign keys, one pointing to one class and the other one pointing to the other class, just like before, just like a mapping table, yes, a mapping class, but additional fields that describe that association. Make sense? Right? So here's, for instance, is an author, and they're writing the book, and they're keeping track of all the logs of, you know, as they enter a new paragraph, or they remove the paragraph, or all the edit logs. Yes, or it could be like an audit table, right? Is auditing when employees that came to work for us, then they left and they came back, and we want to keep track. We have to calculate their Social Security, their Medicaid, and all that based on how long they've been with the company, and we have to have like an audit log of or maybe they move between departments, right? And we're just going to keep track of who their manager was, blah blah blah, right? And yeah, exactly. Here it is, right? So the association class might have, you know, what role do they play in this actor in that movie, right? So if we don't have any of these fields, we draw it like this. So it's only two foreign keys, right, pointing to each other. But if we have just a single additional field, we draw it this way, with a line and then a dash. Make sense? All right. Again, if you look at older class diagrams, they don't distinguish between the two. Right? In older versions of UML, they just do this. They only do this, right? Whether you only have foreign keys or you have other fields, they'll just do this. In newer UMLs, you'll instead find a lot of this. I just wanted to, let you know about the difference between the two. All right, then we have aggregations and compositions, right? So, in those one-to-many relationships, right? In the one-to-many relationships, we might also want to capture the life cycle dependencies between the two, right? Meaning, is the existence of one dependent on the existence of the other? Okay, right? So, for instance, say so I don't like Facebook and I want to get out of Facebook, right? And in my mind, if I get out of Facebook, well, all my content is also removed, right? That's my mental model of what I would expect. So in my mind, this is a composition relationship. If I go, all my content also goes away. So if I don't exist, then none of my content exists either. So for me, my mental model is a composition, right? That data is dependent on the existence of that data is dependent on the existence of other data. Yes? But Facebook's actual implementation is that, well, you can go, I don't care. I'm keeping the content. All right. Yes, I'll remove you from the record, but the content stays. Right. So from the point of view of Facebook, the dependency is an aggregation. There is no lifecycle dependency, right? If you remove one of the records, the other records stay. Yes? Okay. So to capture this relationship is aggregation. We use the open diamond on the one side, okay? And then just align all the on the many side. Like for instance, I make a post, and these are all the comments for that post that I made, right? If I remove the post, might say, well, do I leave the comments or not? Do I also remove the comments? Right? If you think they should be removed, then you're thinking of a composition. If you think that they should stay, then you're thinking an aggregation. And that's entirely up to you. You know, what you want to happen, right? You know, if you think that there is a life dependency, then you do composition, or not, it's an aggregation. So that's aggregation. So for instance, in some cases, it's clearly an aggregation, or it's clearly a composition, right? So for instance, if you have an order and you have a product, okay, you have a record of products, right? You have all the different movies and electronics and all these products, right? And then folks create an order. So okay, give me 3 of those, 2 of those, right? And so these orders might say, well, how many quantity, and it might have a reference to which product you're ordering. Yes, right. So this says one order might have many products in that order, right? Order 1, 2, 3 might have product A, product B, and then order 2, 3, 4 might have product X, Y, and Z. Yes. So what should happen if somebody cancels the order and I delete the order from the record? Should the products be removed? Not. It makes no sense, right? Why would I remove these? I'm just removing the fact that you wanted this and now you don't want it anymore, and I remove it. So that's clearly an aggregation, right? I have a reference to them, but if the reference goes away, the original stays, right? So that's clearly an aggregation, and that's how you would capture it, right? With the open diamond on the one side. Okay. How are we doing with time? Composition is when you want to capture the fact that there is a life dependency, right? That you have decided to implement in such a way that if I remove one, well, then the rest have to go away as well, right? Whether it's you might have a page, right, an online page, and then it's made up of a whole bunch of widgets, right? And you might say, well, if I remove the page, what do I do with all the widgets? Should they also stay? You know, maybe if you decide that they should go away and they should also be removed, then that's a composition, right? But if it's a widget that is being used in many different pages, or maybe it's a logo, right? Or maybe there's a footer or a header that you use across multiple pages, then maybe those widgets are an aggregation. I don't remove it. If you remove the page, I keep those widgets because they're being used in different other places. Make sense? It depends what the implementation is. You decide how to do that. Okay? So it's a composition here. If I remove the person, I remove the phone. Yeah, I guess so. You know, would I keep the phone if I remove the record of the user? Probably not. Right. Yeah. So yeah, the audience. As I was saying earlier, right? If you have, you know, in UML, if you establish a many-to-many, you know, that's plenty. You're done in your design. Okay. Then you say there's, you know, one actor is in many movies. One movie has many actors. There's a many-to-many. Boom, you're done. Right. But if the audience is Java or C# or some programming language, you might want to add in there something that might be useful for the implementer, right? You might say, oh, I'm going to implement it with an array, right? I'm going to add movies, and it's an array of movies, or actors, right? And an array of actors. And that's how it's being implemented. But that's an implementation detail, yes? You know, that's the point of UML anyway, right? UML is a language for describing things, for understanding each other, right? And whatever makes it easier to understand, right? Then UML, you can use UML and adapt it as you need it for communication, right? Now, if the audience is for SQL, right, a database analyst, and says, well, how the heck am I going to implement that? I don't have arrays, right? So the implementation would be to have a mapping table, and you would have references, foreign keys, one that points to the actor and one that points to the movie, right? And that's, again, this is an implementation detail. This is how you would implement it. No arrays, right? Everybody good? All right. I haven't looked at the chat. Any questions in the chat? No. Okay, let's talk about data design. Now that we have talked about UML, hopefully that was a review, mostly a review of what you might have already seen in other courses. All right, let's talk about data design. All right, so let's implement. Let's look at our very first implementation, right? And how do we use what we've talked about, right? And actually apply it, right? So somebody might, we'll start with something trivial, okay, and then work our way up. And so we'll start off with saying, you know, we want to design a database where we want to capture CDs, tracks. Well, wait a minute. Does everybody know what a CD is? Okay, I don't know if that's too anachronistic terminology. Yeah, so we have a CD. You know, there's little discs that used to have songs in them and movies and whatnot. And so I have a whole bunch of them still in my house, and I will create a database where I want to store all my CDs and I want to capture, you know, who the band was, the title of the songs. I want to capture all those kinds of things, maybe even the lyrics, right? And I come up with a trivial implementation, right, of saying, well, I'll need a table where I can list all my CDs. And maybe I'll need another table where I can list all the songs in each one of the CDs, right? It'll be a simple one-to-many relationship where the tracks, right, will reference the CD that they belong to, right? So that these 10 songs reference this one CD record, and these other 20 songs reference another CD record, right? And I come up with something trivial as this, right? I come up with the names of my table, CD, and track, and some of the fields I might want. You know, the title of the CD, the release year, maybe the band, the genre of that CD. I'm going to use SQL, right? And so I'm going to have maybe a primary key where I have the CD ID. Then in the track table, I'm going to have a unique identifier for the track. I'm going to have a foreign key, right, that says this track, this song, right, belongs to that CD over there, right? So maybe I can have like 10 tracks having the same CD ID, saying that they all belong to the same record, CD record, yes? And then I have another 20 songs that have a different CD ID, so that all those 20 songs belong to that other CD. Make sense? The track, you may have the track number, maybe the song title, how long, the duration, maybe I could have lyrics, I could have all different things, yes? And I start, it says, I'm happy about my database, right? And I start entering my CDs, yes? I start entering my tracks. And then all of a sudden I find myself that I didn't really think this through, right? Maybe I had a very simplistic understanding of how CDs work and how they're produced, right? And then I find myself like, wait a minute, oh, I found this CD that has the best of CD tracks, right? With various CDs. That means that maybe I burned a CD that have some songs that I copied from one CD, a couple, 3 songs from another CD. Now I have a CD, right? But I have different bands are in there, different genres are in there. They're all mixed together. They don't belong. So they don't fit nicely into my original data type, right? Into my original schema, right? Different bands, different tracks, different genres that are mixed in, right? Different a performer that went off and did its own thing, right? That had its solo career, and then came back, and and maybe they tried all different genres in the same CD. So now all these edge cases, right? They don't fit nicely into my original schema, right? So how do I deal with this? And so as we said earlier, the best way to design something is to not start at the table level, right? Not start at the tables and properties and whatnot. The best way is to start first graphically at the UML level, right? Draw this in boxes and lines. That makes it much easier to visualize, right? And change different things around before I actually start encoding this. Yes, like we say, 1,000. What is it? A picture is worth 1,000 words. So yeah, so first, instead of starting with entities and relationships and attributes, start off with a class diagram. Right? Start off with a class diagram. So again, we want to be able to seamlessly, be able to represent this in different ways, right? And we want to be able to consistently go between English and class diagrams and SQL, and then back to SQL again, right? And seamlessly go between these two worlds, right? So we need to be able to learn how to do this. All right, so first of all, let's consider the UML diagram, right? So we said that relationships are just the lines between classes, right? Attributes describes the different fields inside of the classes, right? And we can use UML to capture all this. So let's take a look at one, something that we introduced earlier this week, right? We're going to be an example that we're going to be using throughout the semester. It's going to be a small university, right? And the university is going to look something like this, right? We're going to have we're going to capture students, right? We're going to capture departments. We're going to capture sections and the courses, right? And we have these relationships. We say that in the department table, we're going to capture all different schools or different departments that are in there, right? Computer science, the drama department, the math department, chemistry and whatnot, all the different. So a table for keeping track of all the departments. We have the students, right? That might have a first name and last name, and when they're going to graduate, maybe their GPA in there. Notice that there's a one-to-many relationship between the student and the department, meaning one department can have many students, right? So presumably the way we'd implement that in SQL is that student has a foreign key pointing to the primary key of the department. But again, let's not look at the actual implementation, right? Let's stick to UML. We also have courses, right? Courses, we have, one department can have many courses, right? So there's a one-to-many between the department and the course. One course can be taught, can have many sections being taught by different professors, right? So there's a one-to-many relationship between here too, right? One course has many sections. And then we have a mapping, right? We have a mapping table here that says that that particular student, right, is enrolled in that particular section, right? Notice that we have a field here. So this would be an association class, right? Not a mapping class, right? So the more modern way to capture this would be to have a line and then dash that dot here, right? That's the more modern representation. But this is an older class diagram using UML 1.0 and not using the newer style. Okay, makes sense? Everybody good? All right. So so this diagram has lots of things in here, right? Obviously, we have the classes, the attributes, we have the cardinality. Let's start referring to these things what they are, right? So the cardinalities, right next to the diagrams, right here, there's ones and stars. We call this the cardinality, and the cardinalities are star means that it's 0 or more, 1 means just 1, but they all have the notation n.m, right? Some minimum and some maximum. Okay, and there's some shorthands. If you say star, it means that it could have the minimum is 0 and the maximum is any number. It could be any number of those, right? Yeah, so star is 0 or more. 1 means that it's shorthand by minimum of 1 and a maximum of 1. And 0 and 1, 0.1 means that it's is optional. It could have none, or it could have at least 1. Or at most 1, right? It's optional. It could be there, not in there. We call these annotations, to annotate these labels to the lines. The one-to-many here that we have department and students, right? We're establishing the fact that one department can have many students. We usually say from 1 to many, but it's also many to 1, right? It could also be used. That nomenclature can be used as well. Right. So we're only looking at some of the more common ones. Many to many. There's a 1-to-1 here saying that one student can have 1 permit they can park here in the university. Right. We could also establish it as a student can have optionally a permit or not. Maybe they didn't pay for the yearly permit, so they can't park in the university. right? So it's optional. We also have many, a student and a department. So in our original diagram, we only have a one-to-many. One department has many students, or like many students today, they might be enrolled in multiple departments, right? They might have multiple majors, right? A double major, or maybe a major and a minor, right? And so it would capture as a many. You know, one student might be graduating in many departments, right? Now we say that we say that the relationship has a strength, right? The relationship has a strength. If you know exactly how many are participating in the relationship, we say that the relationship is strong. Okay. If you don't know how many, right? Maybe it's optional, it's not required, or star, we say that it's weak. Right. So if you say a one-to-many, that's a strong to weak relationship. Right? If you know that you have the car has 4 doors, right? But I don't know how many USB ports. There's lots of ports. So 4 to many, right? That's still also strong to weak. That's just nomenclature. And so many is also referred to as a weak to weak relationship. One-to-one is a strong to a strong relationship. Just some jargon. So these are some of the more common ones, right? Weak, strong, like star to 1, 0.1 to 1. Those are all weak to strong, or strong weak, one to many, or 1 to 0, 1, or weak like star to star, or star to 0 or 1. Those are all, or strong, right? You know exactly there's a 1 and 1 on each side of the relationship, or 2 to 4. It's also strong. Again, jargon. All right, so reading the class diagrams. So from the visually looking at the class diagram we saw earlier, we can read certain things. We can answer certain questions, right? We know that students are enrolled in sections of a particular course. We can determine that, you know, or all the courses. We can ask the database, you know, what are all the courses that a student is enrolled in. We can determine, you know, which professor taught which course or which section. You know, what's the size of the course? How many people are in a particular course? We can answer those things. They're in the database. We cannot answer. The database is not capturing any information to answer, for instance, if a student changed from one major to another major. It's just not captured in the database, right? Or maybe if a particular professor is advising a particular student, it's just not captured in the database. It was not in the requirements. We never thought of a column or a table to capture any of that, right? But typically, by looking at visually, you can discern what can you answer, which question can you query, and which not, right? And that's very important. It is because you knew the requirements that you came to the conclusion that that is your design, right? It's not that you made a design and then, well, what can I answer? What can I ask my database, right? Ideally, is because there were some requirements. Somebody told you how folks are going to use your database, what kind of question you want to be able to ask your database, and that decided what are the tables and the columns that you needed, right? Not the inverse, like I did, right? I started with my CDs and my track. I started implementing it, and then I ran into an issue that, you know, I have all these edge cases that I just can't put in my database. You know, I did it backwards. I first have to think of what it is that I want, identify all my edge cases, and then decide what the database that I'm going to use. Yes, but you know, as engineers, we often do that, right? We're too eager to start coding, right, without thinking about how is this going to be used and considering all the edge cases. Yes, right. For that, we need the business guys, right, to tell us. You know, we know the how. We need somebody to tell us the why, right? So yeah, so let's go back to this and see some of these some of the equivalences between this class diagram and the equivalent set of tables. Right? What are the tables look like for this class diagram? Right, so first of all, let's look at the cardinalities, the one-to-manys. Right, let's look at the one-to-manys. We have one-to-manys all over the place, right? What would that look like? How would that be implemented in a relational database, right? Well, typically the way this would be implemented, you know, to go from a one-to-many between a course and a section, the way to implement that is to have a primary key in the course, yes, and then a foreign key from the section referencing the course. See that? Same thing here. Wherever you see a star, that's kind of telling you that there's a foreign key there, right? Referencing some primary key in this table, right? And you'll see me a lot going back and forth between classes and tables, and then tables and classes, right? At some point, they should kind of meld one into the other. We should be able to think and design it in a class diagram, but immediately start thinking of how is this implemented as a table, and vice versa. Okay, so wherever you see a star, right, that means that there's going to be some kind of foreign key, right? So for instance, this is what the data might look like, right? For the students, you have a list of what is this? Can I close that? Yeah. So the table of students might have Alice, Bob, and Chuck with the student IDs, right? In the courses table, you might have web, software engineering, databases, and debate, right? And these are the course IDs, right? These are the sections. So for instance, you might have two different sections for web, right? And you might have two different sections for software engineering, 4500. See that? Okay. In the enrollment, right? Notice that we have two foreign keys. One is pointing to the student ID 123, which is Alice, yes, and referencing the section 321, which is this one over here, 321, which happens to be in 5610, right? So we know that Alice is enrolled in CS 5610. Okay, so this is what the data looks like, right? And we understand that these are the ones that are listed as blue are foreign keys referencing fields elsewhere, right? Right. So yeah, so these student IDs here are referencing that 123 over there. So Alice is actually enrolled in 321, which is CS 5610, and 567, which is 4500. Right. So the same student enrolled in two different courses. We have these three different students: 1, 2, 3, 3, 4, 5, and 4, 5, 6. So Alice, Bob, and Chuck, all of them enrolled in the same section, right? 4, 5, 6, 7, which is 4500. So we have Alice in two different sections. And we have three students in the same section, right? So this is capturing all this here, right? And then referencing the 5, 6, 10, and then this referencing the department. Yes, that are all in the computer science department, right? Right. Yeah. So table and classes, we need to be able to get comfortable with going back and forth between UML and tables, and then from tables back to UML, right? We want to do the design in UML, but also be thinking that this is going to be implemented in SQL, and that certain things that we can do in UML actually don't necessarily map directly. So we need to finagle there, right? We need to reify sometimes, right? That we need to bend a little bit UML so that it's useful for us in SQL. Okay. So yeah, we want to be able to go back and forth between class diagram and the relational model. The relational model is the tables, right? In both cases we are modeling, right? Over there we're modeling visually. Here we're modeling with tables. Okay. Yeah, and the mapping is that classes become tables, attributes or properties become fields or columns, right? In relationships, the lines between the classes, they become foreign keys and primary keys. Yes? And we want some kind of algorithm that allows us to go between these two worlds. All right, so let's revisit the schema of our CDs again. Let's revisit that. So yeah, so we have the CDs. The title, releases days, and whatnot. We have the tracks. Let's add lyrics in there. Let's add lyrics in there. Okay. Now, one thing that the nomenclature that I'm using here is that if it's bold and underlined, it means it's a primary key. Right. So CD ID and track ID are both primary keys. If it's italic, it's a foreign key. Right. Well, here's a weird one. Right, this is bold and underlined, which is the primary key, but it's also italic. So it's not only is it a primary key, but it's also a foreign key, right? Let's explore that a little bit, right? So first, let's look at these two, CDs and track, right? So yeah, just a second. Let's yeah. So one CD can have many tracks, and with lyrics, right? If we go back to lyrics, if you have a song, presumably that song only has one lyric, right? Only has, those are the words for the song. You can't change them. If not, it's just some other song, right? So that means that this is what we're going to be doing here is that, yes, we have the data here for the lyrics and the author and whatnot, but there's only going to be one of them. So the relationship is not one to many, it's one to one. If you have one track, it can only have one lyric. Okay, so how do we implement that? And the way to implement that is that not only are we going to have it's a foreign key, which is referencing the track, but because we want the uniqueness that the lyric cannot repeat, we also make it into a primary key. So it's a foreign key because it references the track, but because we want it unique, we also make it into a primary key. So it cannot repeat. Make sense? Right? So yeah, so the lyrics hold the lyrics, blah, 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 and it's both a primary key and a foreign key, and each track can only at most have just one lyric. It makes sense. And so so many tracks to one CD, but one lyric to one track. Right? So we are enforcing certain things, right? That can repeat or not. Right? So one CD can have many tracks, one track can only have one lyric. So it would be something like this, right? You have a whole bunch of records for the track, right? And you know, 3 of the tracks are related to CD number 1, 2, 3, whereas these 2 tracks, the last 2 tracks are referencing CD 2, 3, 4. Okay. Now for the lyrics, the same tracks over there, 1, 2, 3, and 2, 3, 4 over here, right? Have a one-to-one relationship, right? Here the lyric is not only is a primary key, which I'm forcing this not to repeat, they cannot repeat, right? And then referencing the track itself. So one track can only possibly have one lyric, right? So I'm enforcing the fact that the songs can evolve over time. Yeah, so the one-to-many between CDs and track, the way that would be implemented in SQL is that you would have a foreign key on the track referencing the CD. So this also brings me to somewhat what we were talking earlier, right? In UML, right? The line and the annotation one-to-many is enough, right? It would be redundant to put here the primary key track ID, right, and CD ID, and it would be redundant for me to put the foreign key here that points to the CD. It would be redundant. The line already tells me that there's a one-to-many relationship. Nevertheless, right, it's not uncommon, right, that if I know that a DBA is going to be reading this, right, it's not uncommon that I would explicitly put all my primary keys everywhere in the UML and also put the foreign keys as well. Right? It's not uncommon to put them there, right? Again, depending on the audience and what you need to add for clarification. All right, so here's my algorithm that allows me to go from tables to classes. And then later on, we'll look at an algorithm that allows me to go from classes to tables, right? So if you have tables, for each table, we're going to create a class. That makes sense, right? For each, for the lyrics, the CD, and the track tables, we're going to create equivalent classes. Then, for each one of the tables, T1, if it contains a foreign key, that means it's going to be part of on the star side. Yes. Instead, if it has a primary key, right, then it's going to be just I'm sorry. If it's just going to be a primary key, then it's going to be a one side. Now, if it's both a foreign key and a primary key, then it's going to be a one-to-one relationship, right? It's a one-to-one relationship if it's both, right? So this algorithm allows me to go from tables to classes, right? And when we come back on Friday, we'll talk about how to go backwards, go from classes to tables, right? We need to be able to learn, right, how to bridge these two worlds. All right, thank you. Everybody all set here? Start share.
Fast? Oh my God, what happened? I thought we were switching it. She's like, yeah, I'm gonna get
Thank you.
Thank you.
Thank you. Thank you. Have a nice day.
You too.
Thank you so much, Professor.
Take care.
Yeah.
Here.
Wanted to ask our- Yeah, I don't know. Then it's say that too. I don't know if that. It might be. I don't know.
Hi. Sure.
Have a good day.
Take care. Bye.
Thank you, Professor. Did you see attendance sheet by any chance?
Not for this.
Oh, okay. Just making sure.
Yeah, no, don't worry.
Thank you.
Sure.